Okay, so we're going to talk about electrolytes versus non-electrolytes, and believe it or not, this does have significance in chemistry. You might be thinking it's just something to do with electrolytes in your body, but in chemistry, an electrolyte is any substance that will conduct an electrical current when it's dissolved in water. So that's what it is. So in order for something to be considered an electrolyte, it must have two criteria it meets. First, it must have charged particles that conduct electricity. And second, the particles must be able to move. And I'm going to show you some examples of this because not everybody thinks about like, oh, can the particles move or not? All right, so a good example of a non-electrolyte, something that you've heard of, is sugar. So you can take sugar, you can dissolve it in water, and if we were to put, electric nodes inside of it, the sugar would not light up. A weak electrolyte is something called acetic acid, and then salt, or NaCl, is a strong electrolyte. And these pictures here are showing you a non-electrolyte does not light the light bulb. A weak electrolyte lights it just a little bit, and then a strong electrolyte really lights up that light bulb. All right. In a non-electrolyte, the solute exists as just molecules. So if you take a molecule of sugar and you dissolve it, or I'm sorry, if you take a bunch of sugar and you dissolve it in water, all that it becomes is little bits of sugar, right? It's still sugar. There's still sugar molecules. If you take an electrolyte, like say salt, salt is made of Na and Cl, and that, makes NaCl. But you put this in water, it turns into sodium ions and chlorine ions. So an electrolyte is when there are ions dissolved in water. So we can say that things that are ionically bonded are going to most likely be electrolytes, and things that are molecularly bonded are going to be non-electrolytes. Now, weak electrolytes is somewhere that's going to make more sense when we get into acids and bases. But acetic acid actually exists as both ions and molecules. And I don't want to get into that much now because it won't make much sense. So we're going to check out some electrolytes. So I have them here. I've got a pile of electrolytes that we're going to look at. What I've got here, this thing, right? This has light bulbs attached. It is plugged in. It does have an on and off switch. It's off at the moment. And then these two things right here are my electric nodes. So I'll show you the way it works, all right? So if you have an electrolyte, and I'm not going to go in any specific order, but I'm going to show you the one I was just talking about is salt. All right, NaCl. Now this is a solution of salt dissolved in water. So when I take this solution of salt dissolved in water, and I go here, I can tell that is an electrolyte, right? It lights up the light bulb. So salt is an electrolyte because salt has ions, Na and Cl. And when we dissolve it in water, the ions are mobile. I just want to show you, just so you don't think I'm lying to you, if we have salt, plain salt, and we try to conduct electricity with plain salt, it's not going to work so well, okay? Not electrolyte, all right? So all I did was prove that solid salt is not going to conduct electricity. That's why I have this rinse water here. so that I can rinse this off. And you can see here that look at my rinse water has become an electrolyte because I have it kind of set up that way. All right, so let's talk about other electrolytes. All right, another one would be magnesium chloride, MgCl2, is an electrolyte. Well, yes, it is. Stop it. That is terrifying. Sorry, somebody's playing a joke on me. All right. Now, if I take an organic compound, this is hexane. I can show you that hexane, not very exciting, it is a non-electrolyte. Okay? Hexane is a non-electrolyte. Rubbing alcohol, gotta find it. I know I had some. There it is. Rubbing alcohol, this would be like isopropyl alcohol. It stinks. You buy it at the drugstore. This is also non-electrolyte. So these are hexane and rubbing alcohol are both molecules dissolved in water. Now I don't have sugar water, but it would do the same thing. It would not light the light bulb. All right, I like this one. This one is acetic acid or vinegar. All right, this is the one that was in the middle of that picture. It is, actually it looks pretty strong here, but it should be a weak electrolyte. But it's looking like it's a strong electrolyte. And I'll show you as compared to hydrochloric acid. Hydrochloric acid is a very strong electrolyte. So this one is supposed to be weaker than that, although I did feel like maybe I was going to electrocute myself. I've got another interesting one here. This one is copper chloride. So it's ionic. It's an ionically bonded thing. It looks like, I don't know, like a powdery stuff. But when you go to dissolve it in water, it doesn't dissolve. It's hard for you to see, but it's all sitting at the bottom. So it's ionic, but it does not dissolve in water. So non-electrolyte. So just because something is ionic doesn't necessarily mean that it's an electrolyte. All right, now I want to show you one of my favorite things is tap water. It's just water. So a lot of people will say, and I'm rinsing this out, but a lot of people will say, when you ask someone the question, does water conduct electricity? Most people will say yes. I have been told, don't take a bath with a toaster, okay? Water and electricity don't mix. Your whole lives you've been told this. But according to science, water, this is tap water, is a non-electrolyte. Water does not conduct electricity. Now, if I lower the resistance by unscrewing one of these light bulbs, all right, what I've done is I've just made it way easier to light the light bulb. Since this is tap water, this does have some stuff dissolved in it, especially here at Troy High, people say the water's dirty, fine. So, can you see it just a little tiny, tiny bit? It's actually, tap water is a very, very, very slight electrolyte. So don't run home and take a bath with a toaster, because tap water has impurities such as metals or different salts dissolved in them, especially if you're taking a bath with a toaster. You have salts on the outside of your body from sweat. All right, now for our grand finale here, usually when I say the words electrolyte, people think Gatorade, Powerade, because you've heard it in commercials that they have electrolytes and the electrolytes replenish your body and stuff. So I've got Powerade, blue Powerade here. And so the question is, are they lying to me in the commercials, or is Powerade in fact an electrolyte? It is. Little bit. You can see it's not as bright as some of the other ones, but it is an electrolyte. It contains salts. I think that magnesium chloride, calcium chloride, those salts help the nutrients get absorbed into your body. Here, I'm just rinsing that off. Another electrolyte product that you might have heard of is Pedialyte. This is knockoff Pedialyte, but says it's a pediatric electrolyte. So this is what you would give to a baby if they have like diarrhea or stomach bug issues. If you've ever tasted this stuff, it tastes terrible. Is it an electrolyte? Here it is. Yes, it's a major electrolyte. So if you are in fact dehydrated from being sick, you don't want to have Powerade or Gatorade, you want to have Pedialyte. The other thing about Powerade and Gatorade is that it does contain a lot of sugars. Okay, so let's take a look at some math that we're going to do with concentration. So if I were to say to you, all right, I'd like you to make some Kool-Aid, and I'd like you to make that Kool-Aid very concentrated. You would know what that means. You're going to take a lot of Kool-Aid, and you're going to put a lot of Kool-Aid powder into the water, and you're going to make it highly concentrated. Sometimes they sell soaps, detergents, concentrated, they call it. And there's more that's in there. Well, chemists have to have a way to measure this concentration. And you can see here, this picture is of a mole, of course. So the mole is back. All right. Concentration is a measure of how much solute is dissolved in a solvent. And this is a great particle drawing to show you this. So these two flasks or beakers have equal amounts of solute. Okay, let's say they both have 5 grams of salt. But what they have is different amounts of solvent. And in this case, probably water. It's going to be salt water. So the one on the left is more concentrated than the one on the right. So concentration is going to be how much solute per solvent. And we call this molarity. Molarity is the most common way that a chemist is going to measure concentration. Molarity has a capital M, all right? And this capital M stands for the word molarity, and it stands for moles of solute over liters of solution. I was just explaining to you an example where I used grams of salt. If you have grams, you're of course going to have to convert that into moles in order to do these problems. So the unit is moles per liter. I am very brainwashed. When I see a capital M in my head, I think moles per liter because it's easier for me to say that. So this solution has a volume of 2.0 liters and contains 36 grams of glucose. I'm giving you the molar mass of glucose. What is the molarity? So take a second, see if you can figure this one out on your own before I've even shown you any examples. Okay, so hopefully you gave it a try because you really, like I said, you already have everything you need. You know that molarity equals moles of solute over liters of solution. I know here that I have grams. So step number 1 is that I have to convert grams into moles. So I have to say, hey, there's 36 grams for every 180 grams. That is equal to 1 mole. I still write that out for you. You don't need to write that out every single time. If you're not needing it anymore, that's okay, but I will forever kind of do that. So we have 0.2 moles. And then it says that a molarity is moles per liter. So we have that many moles. I'm going to go ahead to the next step, divided by 2.0 liters. divided by 2.0 liters, and I get a molarity of 0.1, right? So molarity equals 0.1. Let me show you the units for this. You can write molar, that's a unit, capital M, or you can write 0.1 moles per liter. So that's the molarity of that solution. Another example, how many moles of the solute are in 250 milliliters of a 2.0 molar calcium chloride solution? And then there's a second question that says, how many grams is this? Again, give it a try. You know everything you need to know to answer this question. It's just working with numbers. Okay, so this one says, how many moles of solute are there? So we need to kind of work this one backwards. My equation right now is molarity equals moles over liters. But in this case, they've given me the moles and they've given me something very close to liters. They've given me milliliters, but, or I'm sorry, they've given me the molarity, but I'm missing the moles. So the moles is what I'm missing here. So in order to solve for this, you're going to multiply both sides by L. Okay, this gets L off the top. So you're going to get molarity times liters equals X or question mark moles. All right. Now the other problem with this question is in milliliters. So I need to convert that to liters. So move the decimal place over, 0.25 liters. So you get a 2.0 molar solution times 0.250 liters equals, so 2 times 0.25 equals 0.5. All right, 0.5. Now, I did screw this up last time and I don't want to mess it up again. You should have the right number of sig figs here. So this number has 2 sig figs. This one has 2 sig figs. This number should have 2 sig figs. So this is 0.5 moles of this that are the solute in this solution. Now I'm not quite done yet because it wants to know also how many grams is this. So this is the answer to the first question. But I also want to know how many grams. So I have to go through and I have to convert. 0.50 moles are in this solution. And what I'm looking at is calcium chloride. So I need to go to my periodic table. Got one back here. Calcium is 40. Chlorine is 35.5. There are 2 of those, so 35.5 times 2 plus my calcium, that's 40. So calcium chloride has a molar mass of 111 grams per 1 mole, right? My moles are going to cancel. That 111 times 0.5 is going to give me my grams, which again, I want to keep the correct number of sig figs, which is 2. That's going to be 56 grams of this, right? 55.5 turns into 56 grams. So I want to go back here for just a second, just to revisit that sig figs. We've got 2 sig figs. This one has 3, this one has 4, but it's that 2 sig figs I care about. So this should be 0.10. All right, you should have that 0.10 there. When a solution is diluted, okay, when you take water and you add more water to whatever that saltwater solution is. The moles of solute don't change. That's called dilutions. So you're taking whatever very concentrated salt water and you're adding more water to it. You still have the same amount of salt. The amount of salt has not changed. The beginning, more concentrated solution, the words we use for it, we call it a stock solution. And we have these back in our cabinets. Like I have a stock solution in the back of hydrochloric acid. The hydrochloric acid I have in the back is 12 molar hydrochloric acid. It's very, very, very strong. For labs in here, all I ever use is maybe like 1 molar. The most concentrated I ever use is 6 molar, and I use as little as 0.1 molar. So what I have to do is in the back, I have to dilute the 12 molar stock solution. Other places that you've seen dilutions before that you don't even realize it, is that acetic acid, vinegar. When you buy vinegar at the store, sometimes you'll see the side of it, it'll say like 96% or something like that. That means it's 96% water. There's a ton of water in it. It's very, very, very diluted. It says like 96% diluted or something. I don't use that value, so I don't know a lot, but it's very diluted acetic acid that you buy. So the formula that you use for dilutions is really, really, really easy. Capital M for molarity. So it's the molarity times the volume of whatever the first one is equals the molarity times the volume of whatever the second one is. The volume can be in liters or milliliters or whatever else you want, as long as these are equal or have the same unit. Okay, concentration will decrease while the volume increases. So in this example, we have a 2.5 molar stock solution of K2CO3, and it's used to prepare 500 milliliters of a 0.8 molar. How much of the stock solution is needed to make the dilute solution? So let's run through all of our variables. The molarity of the initial stock solution is 2.5 molar. Okay, the volume of the initial stock solution is what I don't know. I don't know how much I need to dilute it. But I do know what I'm going for. I'm going for a molarity of 0.80 molar. And I know that I want to have a volume of 500 milliliters. So this value right here is going to end up in milliliters. So you just do M1 V1 equals M2 V2. In this case, we're solving for V1. Divide by M1. Divide by M1. You can rewrite this if you want. V1 equals M2 V2 over M1. And that's what I put into my calculator. So I get 0.8 times 500 divided by 2.5. So how much do I need of the original? I need a volume of 160 milliliters. And I'm going to check my sig figs this time. I've got 2 sig figs. So I want my answer to have 2 sig figs, which it does. So here is another one, 50 milliliters of 6.0 molar NaOH solution diluted to a volume of 750. What is the new concentration? So take a second, see if you can do this one on your own. Practice this. So take a look. We've got the initial molarity is 6.0 molar. You've got 50 milliliters of it. Now you're going to put more water in. You're going to dilute it. It's going to go to 750. We want to know what the new molarity is. Think about this logically. We know that when you dilute something, the molarity goes down. So hopefully, if I did this correctly, I should get a lower number. So I rearranged the equation, got V2 on the bottom, M2 equals M1 V1 over V2. So I've got 6 times 50 divided by 750. All right, so my molarity went pretty far down. It went from 6 molar to 0.4 molar. Want to make sure I keep those two sig figs. So 0.40 molar is my new molarity. So for the last thing, I just want to point this out to you. If you're preparing solutions, right? If someone gives you, this is called a volumetric flask. It's a way that we prepare solutions. When it's saying that you want to make a 0.77 molar solution of NaCl and you've done the math and you've figured out, well, how much do you need? Well, you need 45 grams. I just want to remind you, it's not 45 grams plus 100 milliliters or 1000 milliliters. Instead, it's 45 grams and then you fill it up to the top. All right, because you want to get the milliliters of the total solution. Nowhere have I mentioned solvent. It's not moles of solute over liters of solvent. Molarity, capital M, is moles of solute. That in this case would be the NaCl over liters of solution. All right, not liters of solvent. So the solution is NaCl plus water. So just kind of a picky thing that I wanted to remind you of when you're doing this.